Everybody's doing good? All right. Wonderful. Blockchain. Okay, thank you so much for coming out. Wasn't expecting this kind of turnout. Tried to get my wife to come out, even she said no. So thank you so much for sacrificing your Saturday afternoon to be with us. My name is Shivam Saxena. I'm a professional engineer registered here in the province of Ontario. And it's just such a pleasure to be here with you today talking about one of my passions, which is smart power grids and clean energy. So I'm here to share this knowledge with you today, as well as how we can merge blockchain applications with this application as well. So quick shout out to the Blockchain Lab. We've got Professor Henry Kim and Merrick in the house. A quick email in 2017 to the Blockchain Lab enabled this type of collaboration. At that point, I didn't know anything about blockchain. Even now, my knowledge of blockchain is relatively limited. But thanks to these gentlemen for equipping me with the right knowledge and the tools to go out and implement a project such as this, to have a real-world implementation for a blockchain-enabled power system. So thank you so much to the Blockchain Lab, as well as York University. I'm under the supervision of Dr. Henny Farag, who's my PhD supervisor. We've got two gentlemen from his lab here as well today. So it's been a great collaborative project over the last 2 years, and I'm excited to display the results with you today. So, by the way, I like to run really interactive sessions. So if you have any objections or questions or things you want to comment on, go ahead. I'm all for active discussion while we present these topics. So, quick outline of what we need to get done today. I'm going to spend as little as possible on the speaker introduction, really get into a primer of what smart power grids are and what this new concept of transactive energy is. Then we're going to try to relate the needs of the current smart grids with how blockchain can solve certain business cases and certain problems that smart grid operators are facing. And then we're going to get into the case study of how we implemented a blockchain-based transactive energy system in a real-world Vaughan microgrid. Okay? So before I get into me, I just want to get a quick profile of the room. How many people are aware of how energy flows from power stations to your door? So some. We've got two PhDs in the house that can help me. Okay, perfect. So I'm going to proceed at a relatively medium pace. Tim, I've got 40 minutes? Yeah. Okay, all right. I'll try to keep the time going. All right. Yes, so a little bit about me. I am the systems architect and CEO of a company called Hero Engineering. I founded it in 2015, so we're into our 5th year. Our mission statement is take the fight to climate change, and we do that by developing products and doing research in clean tech and particularly smart grid applications. So as you know, the world of distributed energy resources is exploding. People are getting into solar energy, electric vehicles, and batteries. And all these things are causing problems at the grid edge. We're going to review that in a couple of slides. But there is software that's needed to coordinate the objectives of you as the owner of those DERs with real-time constraints that grid operators actually have. So this is the industry and application that we work in. Okay? I'm passionate about the environment, passionate about electric power grids, and when I'm not coding, I'm usually playing sports. As I mentioned earlier, in my 2nd year of my PhD as well, so there's a lot going on. So this is a slide I try to use in all of my presentations. This is really the end game. This is the biggest business case of all, climate change. We have to get our act together, every single one of us in this room, okay? Power generation, transmission, and distribution accounts for upwards of 30% of all carbon emissions, and we know that carbon emissions is the major driver of climate change. And all the extreme outages or the weather events that are happening over the last couple of years are indicative of this. Whether it's atmospheric pollution, cyclones, sea level rise, all these things are related to climate change, and we, everybody in this room, and all the politics, and everybody across the world is responsible for this. Okay? Power systems or energy systems are particularly vulnerable because they're centralized in nature, right? Hurricane Sandy, Toronto floods, wherever cyclones are coming through the world, we leave people without power. And when we leave people without power, all productivity stops. So in the US alone, power-related outages cost over $10 billion annually in terms of economic development and sustainability. So there's a big business case for how we can decentralize these systems, increase robustness and reliability in power systems. Now, a little bit of review for power systems. Power systems are divided into three general components: generation, transmission, and distribution. In generation, we have centralized power plants, mainly coal, nuclear, natural gas. These humongous power systems, we take the power, we step it up the voltage, and then we go across to very, very long distance transmission lines. Then it gets stepped down into these things called distribution feeders. So you might see them above on your house. See the distribution lines? That's feeding power into your home. So 1 watt of power, everything we're using today, it's quite a complex journey from where it actually originates. But what I want you to take away from this slide is that it's very centralized in nature. Any one attack or any one outage on any one of these interconnected systems, and we have a big problem. Today, we're going to be talking mostly about distribution systems because that's where you and I are connected, at the end of the line. Now, we can forget about all the main terminology, but the main takeaway I want you to take from this slide in distribution systems is that we exist all the way at the end as end consumers, and power flow is unidirectional, all the way from the utility, your local distribution company. If we live in Toronto, it's Toronto Hydro, Vaughan. Then you have Electra. The person that actually, the company that gives you your energy bill, that's your distribution utility provider. Okay, power flows from their substation to you, unidirectionally. That's generally how things go. Okay? Now, one of the big problems for, we call them DNOs, distribution network operators, is these feeders. These primary feeders. Now these feeders, if you imagine like the 401 has traffic, right? There's a certain capacity of traffic it can take. It's the same thing with power systems. That distribution feeder can only take a certain amount of power flow. So when there's too much load by us at the end of the lines, traffic stops. And what I mean by traffic is power. Active power actually stops, and that feeder gets congested, similar to how the 401 gets congested. Okay? Now, when that happens, bad things start happening. A lot of heat accumulates in those distribution feeders. We get power losses. And more importantly, the quality of power that we have at the end of the line starts to go down. Lights start to flicker. Maybe if you have a cottage and a heat pump stops working. So we have all these issues when there's too much congestion on the feeder. Now, usually, distribution network operators, DNOs, they sit in a control room. They've got 24/7 operation. They have three main objectives. One, reduce peak demand to avoid that feeder congestion I just talked about. Okay? That usually only happens 3 to 4 days a year, usually in the summer when it's extremely hot outside and everybody's got their AC cranked to the max. Okay? So we want to reduce that peak demand. That's really their only motivation in life. That's all they care about. Okay? Second, we want to reduce GHGs, greenhouse gas emissions, by limiting power generation of dirty sources. So sometimes when the congestion's at its peak, if a utility has a natural gas generator, they'll actually turn it on. It's very quick acting. And that feeds local power to sources. It takes some of the congestion off the line. It's like if somebody built a little freeway to a freeway on the 401 and allowed traffic to flow. That's pretty much what it does. Okay? But really, to summarize, the DNO's objective is to manage supply and demand of electricity at all times, 24/7. Too much generation, there's a problem. Too much demand, there's a problem. They want to balance it 24/7 all the time. This is supposed to be a solar panel. Sorry, guys. It got cut off in the Google transmission. But now there's these new resources called distributed energy resources. And we all know them and we're all familiar with them. Solar panels, energy storage systems, electric vehicles, and smart loads. What I mean by smart loads are those Google Nests in your home that allow you to remotely control how much energy you want for your heating systems. Those are smart loads. And all these resources can really help us and the power systems manage that peak demand. Okay, so if I'm a customer, a big factory, and I've got a process that consumes a lot of energy, I can outfit my building with 150 kilowatts, 200 kilowatts of solar, and I can reduce my peak demand to avoid that congestion I talked about. right? Batteries are really interesting too. What you can do is charge them off peak in the night, and when you really need power in the middle of the day, when the price of electricity is at its highest, at peak, you can discharge it. So that way we can shift that peak demand. Same thing with electric vehicles, right? When we use electric vehicles, we can really limit the amount of greenhouse gases that are caused by petrol or diesel or gasoline, whatever the fuel mix is. Okay? So these DERs are really instrumental in making the smart grid an actual smart grid. The grid that we have today is still a legacy grid. It's not that intelligent. There's not a lot of communication going on between the DNO and you. You'll get a bill at the end of the month and that's it. That's really the only communication you have with your utility. But the utility of the future, the DNO of the future, wants to communicate in an automated way with you. They want to take advantage of your DERs, right? They want to have a high penetration of renewable generation. They also want to have decentralized type of applications when there's an outage in the main grid and you can use your resources to island away and make a community of your own. So these are flexible ways in which a smart grid can go and really satisfy those operational objectives that I talked about earlier. Most important is the third point. We want bidirectional power and communication flow. Right now it's just a utility talking to you once a month. But what we should be able to do is say, hey, as a community, we have excess solar. Do you need it? Who needs it right now? Can we inject it to the grid? Can we get a good price on it? Can we sell energy? Can we sell services to the grid? That's the way it should be, but it's not like that right now. As always, there's big problems though, okay? When we have DERs on the grid and they're uncontrolled, they cause lots of issues. So this graph on the left-hand side is actual real-world measurements of the microgrid that we work at. It's called the Vaughan microgrid. See the red line? There's something called voltage in power systems. Voltage is the lifeblood of a power system. It needs to be in between this area. Okay, voltage essentially, if you have a pipe like this and water is flowing through it, the rate at the water flows through is like current, but the actual impetus or the potential energy to take that water all the way through, that's voltage. It's the juice in the line that actually pushes that power. So if there's too much voltage and too much juice, there's excess heat, and your entire transformer infrastructure could melt. It actually causes a lot of power losses as well. We operate in the summer 80% over this mark. And as a result, our distribution infrastructure is actually melted. So 2 years ago, there was a heat warning, 35.5 degrees Celsius we reached. On that day, the side of our transformer actually melted. So there's a real-world problem here that we faced. Second is electric vehicles. There's an experiment done in Sacramento. People are rich there, apparently. In an affluent neighborhood, there was, in one community, out of 8 houses, 6 of them had electric vehicles. They all plugged in at the same time, and they did 3-4 week measurements. So you see that line, the red line, 30? That's the maximum power that that feeder can take, and they tripled it overnight because everybody's plugged in at the same time. And their estimate is because of that, in the city of Sacramento, they have to spend $1.5 million to upgrade all their transformers to handle all the capacity charging of electric vehicles. So now we see all this uncontrolled operation really affects power system operators. Okay, remember this? This is the legacy grid. Power flow is unidirectional. Now this is happening. At the end of the line, we are no longer end consumers. We're something called prosumers. We have DERs. We have solar. We have electric vehicles. And we're taking power and we're injecting it back into the grid. And this is precisely the juncture where the utility, the DNO, it doesn't have communication and control infrastructure. Because they never, ever envisioned that this would happen, right? 50 years ago, the price of solar is 2,000% what it is today. Right now, it's about $1 a watt. Back then, it used to be $75 a watt. So nobody ever could predict that people would one day have solar panels on their home. So they never bothered building out this infrastructure. And that's kind of biting them in the bum now. Here's the biggest challenge. Those DERs are owned by you. I don't have an electric vehicle at this point in my life, maybe one day. But maybe somebody does here. People have solar. This is not controlled by the utility. It's controlled by you. And your objectives and the DNO's objectives are different, right? Your objective is to generate as much revenue as you can from your DER because they're expensive, right? If you have a roof right now, standard roof, maybe a 1,500 square foot house, can somebody tell me or guess if I want to outfit my roof with solar and provide maybe 10 kilowatts, how much does that cost? The total installation, start to bottom. Yes?
20 grand.
Very close. Yeah, $24,000. A lot of money, right? So you want to recoup that investment as soon as possible. So you want to take the power that you have and inject it into the grid and get paid for that. But if there's too much power and too less demand, we get those voltage problems that we were talking about, right? So the utility objective is to curtail you and say, no, limit yourself to 25% or 30%. So we see this conflicting set of objectives that are causing all these issues at that grid edge. So we start talking about a concept called transactive energy. And what we see now is because the grid is decentralizing, decentralization needs trust, right? So the responsibility of a safe and reliable power grid, that's not just the DNO's responsibility anymore. It's actually ours too, because we're part of that problem, right? So transactive energy is all about, hey, can I, as a DNO, can I incentivize you with the electric vehicles to maybe not charge at peak times? Or maybe if I have a battery, can I ask you to discharge it when I'm in trouble? And I'll pay you for your time, and I'll pay you for your services. This is transactive energy. Fundamentally, the combination of economic and control techniques to improve grid reliability. It's about creating a marketplace that we can all exist in together. Any questions so far? Clear? All right. What are the ethos of TEF, Transactive Energy Frameworks? Number one, high coordination. Okay, one of the issues, like we saw on the slides with solar, is that it's very intermittent, right? We have solar, then there's shading, and it goes down. Even with wind, sometimes there's not. Causes a lot of intermittency. So when we go and we try to depend on more than 30% solar in the grid, bad things start to happen, right? So we need high coordination of all these resources to follow those generation patterns. I'm going to slip ahead to point number 4 shortly. We should maintain system reliability at all times. That's obvious. But since here we're talking about Hyperledger and blockchain, I want you to focus on points 2 and 3, and specifically the bolded ones. Non-discriminatory participation of all users. Number 3, observable, auditable, accountable metrics of participation. All these things, if you're a blockchain enthusiast, they should be making sense to you now. Okay, so before we get into blockchain as a solution, I want to point out that transactive energy is not new. It was first coined in about 2010. There have been solutions out there, both decentralized, IoT-based, and centralized, that have tried to solve this problem with varying degrees of success. How many people know about the Brooklyn microgrid? Some people. Right, good. The Brooklyn microgrid is about, at that time, it was about 2 neighborhoods, one with solar panels, one without, and they implemented a peer-to-peer based trading system, right? So there have been many IoT-based systems like that where you can trade your energy back and forth. Okay, but the biggest problem in non-blockchain based solutions is how do you verify those transactions actually happen, right? Because in peer-to-peer, there's no central database that people can actually access. You need to have history. And for you to expose your history to everybody causes a lot of auditability issues. So that's one reason it hasn't gained any traction. Then people tried to have centralized solutions for this, and then privacy became a problem, right? Now, privacy is a big deal. Because if I have an electric vehicle and I'm giving you my resources, I'm geotagging where I'm charging, and I'm giving you my resources in terms of where I need to go, how much charge I need my battery, you can take all of that information and create a characteristic profile out of me. For example, if I'm charging my electric vehicle at the same church every Sunday, and you know exactly where my charging patterns are, you can determine perhaps I'm Christian, perhaps I live in this neighborhood, and then you can determine my voting mechanisms. All right, and all this privacy can be sold everywhere. And this is a big market these days. So it's a big problem. Number 3 is security and the classic single point of failure. Centralized systems, they get hacked, they get attacked, and they have bottlenecks. So that's why these two approaches have failed generally when it comes to handling transactive energy frameworks. This slide is here just for those that are not familiar with blockchain. Should I spend time on it or should we go forward? Everybody generally gets what's going on here? Yes? Okay. So in general, why do we use blockchains? Blockchains, in our case, in the transactive energy case, it's used when a group of peers must work together, but they do not necessarily trust each other. We like to call it a shared business network, right? So what is blockchain? It's basically a distributed shared ledger, right? It's a ledger where there's a mass of data, and everybody in the room, let's say we're all part of this blockchain, we're all validating the transactions that go onto those ledgers. So there's consensus-based mechanisms to make sure that all data going in and out and the actions taken on that data is true and verifiable. Second is automation. There's actual code that lives in the blockchain called smart contracts that can take action on that data and make decisions for you in an automated way. That's what blockchains are according to my understanding. Okay? So how does blockchain actually solve issues that we encountered in the previous slide? The shared ledger concept provides a single point of truth because peers are verifying those transactions with each other based on consensus. Okay? And as a DNO, that's the biggest thing. At the end of the day, when they do their accounting, they need to know where energy came from, where it went, what the losses were. And we, now that we're part of this ecosystem, we need to know that as well. So blockchain is a good way to provide consensus on that. Second is, in some blockchains, you can actually provide read-write mechanisms on the data you're posting to the ledger. So that solves some problems when it comes to privacy, in particular GDPR, which specifies the right to be forgotten. So if I've entered into a framework and I spent some time there and I've contributed my personal data and I want to leave, I have the right to be forgotten. So blockchains can help with that. Third is that blockchain architecture is fundamentally decentralized. So we've gone past that single point of failure issue. Okay? Now, returning to blockchain compatibility with those ethos that we discussed earlier, blockchains are non-discriminatory because we've got consensus-based decision-making based on peers. Number 2, we've got observable and auditable interfaces due to the immutability of those transactions on chain. Number 3, if we want to hold people accountable, maybe for bad data, or perhaps you promised your utility that you wouldn't charge a peak demand, but you did, we've got smart contracts to enforce penalties on that as well. Okay, so we see this system in which we've taken trust out of the scenario. We've actually allowed utilities to now trust these DERs. And before I go a little bit further, I just want you to understand the mindset of utilities, right? Utilities, over time, they were monopolistic entities, right? They handled generation, transmission, distribution. They ruled the roost. There was no competitive advantage, nothing. It was just them. Then in the early 90s, there was deregulation, and there began to be a lot of competition. So now the utility is a service, right? As a result, the utilities have a tough time trusting different people to provide services, right? Now you're coming in with your electric vehicles, your solar, your batteries, and you're saying, utility, I can help you actually fulfill your operational objectives. And they have no way to trust you. They don't want to trust you. And why should they? This is millions and millions of dollars of infrastructure on the line, right? So if we can introduce a system that takes trust out of the equation, then we're in business. Okay, now getting into the mathematics. At its core, transactive energy frameworks are a marketplace. That's all they are. Their ability for you to provide energy and services to a grid operator. So what we've done is taken a smart home concept where a smart home consists of solar energy, electric vehicles, a smart thermostat, and a battery, all in one home. And we've allowed you to place energy bids for each one of your DERs. Okay? So if your battery needs a certain amount of energy, you're allowed to put in a price quantity pair represented by these lines, horizontal and vertical. And within a retail marketplace, which is usually 8 homes and a local transformer, you can trade your energy with everybody else. So it's a classic case of peer-to-peer energy trading. How it works is all the generational sources we stack on the left-hand side from bottom to top, and all the loads we stack from top to bottom on the left-hand side. And where they meet in the middle, the supply and demand of electricity, is the market clearing price. So where supply and demand meets, that is the most equitable price of electricity for that community. It's called the market clearing price. Okay? And already we can tell that when we're playing with this kind of money, we need this to be done in a trustless, decentralized way that's not run by one operator. Any questions on this slide? Is it clear? Okay. Oops. Oh, one more thing. See here MCP1 and MCP2. We noticed that MCP2 is a lot cheaper than MCP1. Can anybody tell me why?
Time of the day?
Has something to do with that, yeah? Do you have an idea over there?
It just looks to me like if you're going up, you're curtailing load there, right? So the load for a certain price will curtail, and then you've added this extra BESS.
Yep.
1 and 2 versus the unmovable grid or something?
Yeah, you nailed it right there. So the more locally sourced energy that we have, the best, as in the battery, the solar, all the way, the more contracts that can be had, right? At this market clearing price, only this and this operate because they're at the market clearing price, right? Load 1 and load 2, they get their loads on, and then these two, and then we're done. All these guys are off. All these guys are on, okay? And this market clearing price, because we have more local generation, we allow more local loads to come on. So the whole idea is that we generate more local energy, we consume more local energy, right? We reduce the congestion on those feeders. That's the whole idea. So you're right. Does that make sense? A little bit more sense now? Okay, perfect. Last thing, we can talk about characterizing these bids. We characterize them as selfish or helpful. Okay? Now this is an energy bid. What really is an energy bid? It's sacrifice on what you perceive to be something that is a benefit to you. Okay? So for a smart thermostat, it's thermal comfort. So imagine it's a really, really hot day. It's like 35 degrees Celsius. Okay? Everybody's got their AC on. The feeder congestion is high. Okay? So utility will send you a message and say, hey, for those of you that have smart thermostats, how many degrees are you willing to sacrifice your optimal set point? And we'll give you money for that. So the way we can characterize is this. This x-axis measures the temperature deviation from your preferred set point, right? So if I want the temperature in my house to be 20 degrees Celsius, this is the maximum I'm willing to go, 1.5 degrees or 1 or 0.5. So we see two types of curves here, right? We see the orange curve and we see the purple curve. You notice how the purple curve breaks at 0.5 and goes all the way up? What that's telling you is the maximum I'm willing to play with my smart thermostat is 0.5 degrees. At that point, I'm willing to pay whatever price it takes. So I'm selfish in that case. I don't want to play with my smart thermostat because I need that thermal comfort. Whereas a helpful bid curve is a lot more flexible. It's not rigid. At this point, that break-even point is 1.5 degrees. So this bid curve number 2 is a lot more helpful, and it's willing to sacrifice a lot more thermal comfort to allow for more financial incentives. I'm probably the most frugal man in this room. I like to save money as much as I can. So my bid curve would be somewhere around here, like 3, 4, or 5 degrees. But here, what we can do is characterize all these bid curves and allow the utility some sense of flexible demand. Okay, Any questions? Okay, now getting into Hyperledger. How do we translate all the theoretical knowledge that we just gained, and how do we translate into Hyperledger? Okay, so I think Laszlo was talking earlier about channels. Channels is a really useful system in Hyperledger. It allows you to abstract away different peers and put them into different channels such that they can't communicate. In this case, what we've done in a smart grid of n communities is we've abstracted them into different channels with their own ledger. Okay? And what we've done is we put one utility node in every single channel. So one utility node has observability of all the other channels. But if I live in Vaughan and you live in Toronto, for example, then there should be no reason why we should be communicating, because we're not serviced by the same operator. Okay? Now on the ledger, we store time-stamped minute averages of all the energy that we're dumping into the grid or taking it away. If it's negative, like in this block, that means we're injecting power to the grid. If it's positive, that means we're taking power away. And the HID is a home indicator. It's just an indicator for who you are in the network. Okay? The smart contract has 3 functions. New interval creates a different bidding interval like we saw earlier. Calculation of the market clearing price. You know how we match the supply and demand? That's actually a mathematical formula. So we implement that on Hyperledger Fabric on chain. So all that works on chain. And then we close the interval. We actually close it off on the chain, and nobody can contribute to that anymore. So that's how the smart contract works. And the peer nodes are the gateway from all the smart homes all the way to the blockchain. So there are things called dApps. Maybe they don't exist too much. I think it's more of an Ethereum term. But what we mean by dApp is just the application that you use to interact with the ledger. So we created a dashboard that people can come in and actually program their curves and then go in the microgrid and actually trade their energy. Okay? Okay, so now onto the case study for our Toronto microgrid. This is a nice picture from a drone. It's a nice facility. We've got about 3.5 acres, 100 kilowatts of renewable energy, about 100 kilowatt hours of battery. Lots of space. But you've seen that picture before. We've got a severe voltage problem. In fact, Nader, you worked on this project 2 years ago. Yeah. The reason why is because we have a generation to load ratio of 5 to 1. So our solar panels create so much energy, and there's such less demand that the voltage is out of whack most of the time in the summer. So most of the times we actually have to turn our solar inverters off, or we get some sort of message from the utility saying there's a problem. This is something we power engineers like to refer to as a single line diagram. It allows us to visualize all the main assets in one plane diagram. And here we see the presence of 4 nodes on the network. One is a solar hut. It generates about 30 kilowatts of power, and power that we can control. So usually, like at this day and age, 75% of solar, you can't control it. It just generates. If you want to disconnect it, you actually have to go out and take the wire out. But now there's smart inverters in those solar panels where you send commands and it can curtail automatically. So although there's about 50 kilowatts of solar out there, there's only 30 that we can control, so we'll only consider that. Going further downstream, the distance is about 125 yards. We have wind power, another 20 kilowatts with an active battery energy storage system. And then on another feeder here, we have 2 smart homes. One with solar, one without. So we have a whole bunch of assets to play with. It's actually a really cool microgrid. Also at this microgrid, we have over 750 monitoring points. So for those of you interested in IoT and based applications, we have different IoT-based products that allow you to monitor in real time. And for those of you that want to do any research, definitely encourage you to collaborate. It's a really cool place where you can see your research go to different ends. This is a dashboard I created. You can tell an engineer created it. It's not particularly attractive, but it allows me to control and see everything in real time. So I sample data from all the inverters on these assets in real time, whether they're electric vehicle charging station or their power meters, and I dump all that information to the ledger. So we have 4 nodes actually going out there, minute averaging all the energy consumption, and then throwing it onto the ledger. Okay, so at this point, I'm going to show you a demo. How are we doing for time, Tim?
I don't know. We're good.
Anybody getting bored? Okay, good. All right.
And demonstrating our blockchain-based transactive energy dashboard. The purpose of today's demonstration is to show how different buildings in our microgrid can trade energy with each other and ultimately really maximize the use of.
So, any questions on that? Yes?
I might have missed it, but who's running the nodes on that blockchain?
So in this case, we use Composer.
What entities, like who will be running the nodes?
Okay, in that case, whoever owns these assets, we have a Raspberry Pi connected to all the main ones. So one connected to the electric vehicle, one connected to the smart home, one connected to the Sunny Hut. So whoever has any skin in the game would run nodes. In a utility scenario, then you would get aggregators because it's impractical for one device to run nodes. So there are services called aggregators that aggregate people's small DERs together, and they would run nodes. Yes?
How would you maintain that as decentralized?
Sorry?
How would you make it decentralized?
How would you make which one decentralized?
Decentralization. Would this be centralized?
This is decentralized control. What about it makes you think that it's not decentralized?
Because they still have to be hooked up to some sort of centralized. If they're not hosting their own node, they have to, for example, if they're flying, they'll have to host their own node in order to run the system. If they're not running their own node, they would have to actually run an organization node, an application that's probably centralized. So how
When we refer to decentralized, we refer to the decision-making being decentralized. And even the application entryway, it'll go to a centralized application, but the actual decision-making to take all those coordination, that's decentralized.
But then you said they had with privacy, so what if it's not a centralized body have all the permission of what you're doing?
But they don't have the read-write permissions to do anything with it, right? The only thing that the centralized body has, is the quantity and price and the type of DER. It has nothing else available to it.
The centralized body will know who's putting that at the end of the day, they still know who's putting that input in there. So at the end of the day, they can still figure out what they're doing.
Okay, but first of all, there's no centralized body running the smart contract, right? Like the blockchain is hosting the smart contract that's validated by all the peers inside of it. So there's no one trusted authority that's in charge of running that market clearing price.
What I'm saying is that there has to be an SDK, right? So
Yeah.
if the person not running their own, anyways, we're talking about it.
Okay.
If they're not running their own node, what do you say? If they're not running their own node, for example, I was doing this. I would have to run my own node.
Yeah.
If I'm not running my own node, then I'm using a centralized application.
Okay. Do you have a comment?
Would you say this is less centralized or more centralized than status quo?
This is less centralized.
So more decentralized?
Yes.
So it's an improvement over the current status?
From what point of view? From the trusted type of thing? Yes.
Yeah.
Yes.
So
Yeah.
it is a step forward?
It's a step forward. Yeah. Yeah, for sure. Yeah. Now, does it have its drawbacks in terms of communication latency and all these things? Yeah, absolutely. Yeah. Yes.
My general question here is more of an economic one. Let's say I have surplus power. Like, first of all, if I'm in a city, then the nature of generating power will be more expensive than generating it in a rural area, simply because if it's solar, it's just the price of land.
The price of what, sorry?
The price of land, i.e. I'll have more space to put
Okay.
panels if I'm out there than
Yeah.
if I'm internal.
Yeah.
But my secondary economic thing is, basically, what you're doing is you're taking surplus power and you're selling it to somebody who basically doesn't have enough. My argument would be, when you cover all the cost of the setup and the swapping of the power, it would probably be more economically feasible, profitable for you to just dump that power into some sort of, like, to basically monetize that power, probably through GPUs.
GPUs, like
Just, like, legitimately, like, you've set up this system. If, like, the classic example is mining crypto, but if you're not mining crypto, there's folding proteins, there's a whole bunch of stuff that you can use excess power for to generate profits in a decentralized way.
right.
Wouldn't those, to me, those solutions would actually generate a higher return than actually selling the power?
Yeah, it depends on the business case, right? So the only way this business case is successful is if the utility gives incentives, right, to all these community members. Because I'll show you some simulation results 2 slides down, but you're absolutely correct. Because the price of electricity, particularly in Ontario, is so low, like the wholesale price of electricity, we're not getting much benefit by this selling and stuff. But what's going on is it's getting the utility to not invest in that capital expenditure they need to enhance our system to support all these DERs. That's in the millions of dollars. So from the utility point of view, it's much better to extend into these systems rather than to go into the capex of getting into those upgrades.
That just, and unfortunately, this actually returns to his point, that you more, unless you, this isn't a technological issue, then you're focusing on, you're creating a centralized governance solution that is requiring the people who are generating powers to basically incentivize these people. Like, it's an act of government.
Okay, but at this point, what choice do these DERs have, right?
Like,
I think I understand what your point is now.
like it's just, like, legitimately speaking, like, just because there's 2 factors here, and the power generators don't want to do it. Like, the most economically efficient way for me to do that would just be to tell them all, you guys should buy a GPU and then mine cryptos or full proteins, and you'll make more money than if you sell the money back to the grid.
Okay.
Yeah, just this, but this is not like a money-making scheme. This is a transformation of an energy grid from centralized to decentralized. And it doesn't need to be these people who need to provide the incentives, you're saying?
Yes.
That's maybe one way to look at it. Another way to look at it could be that in the future, we together as citizens will legislate and say, I don't care what incentives you're providing, buddy. The government is changing and transforming the grid.
Right.
It's now going to be more decentralized. We're going to use more renewables. We're going to have more resilience in the system. It's going to be done fairly and what have you, right?
Right.
This is an improvement structurally in many, many ways. Right?
Yeah.
So,
Okay.
I
But
think
the argument is just, I want to make it clear, that's not my argument. My
No,
argument is, if we do all of that, we still do solar, we still decentralize it more, we would still put the solar panels outside the cities. So you wouldn't, you just end up with, it just becomes more economical to be generating power outside of the cities and pulling it in.
There's
than it does to
nothing.
do it at the house level.
Not
There's-
necessarily, because it's hard to build new transmission. So in some sense, once you're melting transformers and transmission lines and you can't get any more right-of-ways on the way into the city, if you reach your capacity, it's sometimes actually cheaper to site generation near to the load.
Yeah.
You have the resiliency thing too, right?
I was going to say, to your point, right? There's nothing more efficient in power systems if you can generate and consume locally. So if you want to do that and not play in this marketplace, that's fine. Just don't bid.
Yeah.
Right? But again, that's under this governance structure that's decentralized. You know what I mean?
No,
Yeah. Yes.
I'm curious about the cost. I actually was a power trader for quite some time, so I know this market clearing price in
Yep.
Ontario. They have local market power, but they don't pay it.
Yep.
They do this constraint on and constraint
Yep.
off stuff.
Yep.
This is interesting because it's pushing it down from the bulk transmission system through the distribution and all the way to the people.
Yeah.
So I find it very interesting. What I'm curious about is the control software that it takes to turn to the dispatch element. So the way these clear, you actually have to get a dispatch, and you have to have some software that does turn you on or turn you off.
That's right.
So what I'm curious about is from a cost perspective, you know, are these batteries in the electric cars, is it costly to interface? Is it like I see you manually somehow turn those big, the load on, the E-load.
Uh-huh.
Did you write that software?
Yeah.
Is there it's something on a solar panel that is easy to interact with to allow it to dispatch on and off, control its load, curtail its load?
Yeah, for sure. So everything that you saw in the video is automated. There are APIs for all the smart inverters as per the new requirements, something called IEEE 1547 and IEEE 2030. They specify that every new DER that gets connected to the grid needs to have some way to control it automatically. So it's easy to interface with those. And also, we don't need to reinvent the wheel. So if we want to curtail at some point some solar, we provide the set point, and the internal algorithm, the inverter, takes it forward. So from that point of view, it's not so difficult to write the code to do that. The E-load, yeah, there's no API. So we had to bootstrap a Raspberry Pi with some electronics and stuff like that.
That's more of my question.
Yeah.
So as you start adding electric vehicles in here, there's a lot of load that's old, like my house, that can't be dispatched.
That's right.
So do you just say they bid infinitely?
Yes, they become critical loads. So similar to your experience in the energy trading system, LDCs are critical loads because they can't manage it, right? So in the bidding system, they bid at the highest point of the bid. So they're always guaranteed the power that it needs.
Which you could have this market sort of, theoretically, it would unload the critical points where you would put the grid operator.
That's right.
Bid in would be the place where it's constrained frequently.
That's right. So yeah.
Presumably, but somebody could screw with it and make those guys pay a lot.
Yeah.
You could have griefers on the system that would.
There are lots of considerations, certainly, yeah. Like what we do in that case to simulate feeder congestion is we make the grid bed vertical. So it constrains everything off.
Okay.
So
Because you know, if everybody on the street has an electric vehicle, just like that thing where it tripled the actual capacity with electric cars, you would actually.
You'd see that.
And a new person was thinking, should I buy a car? You'd want to make sure you communicated that the price is almost always going to be massively high
at peak times
in this particular place because these guys aren't bidding properly.
Absolutely.
And so you force a lot of consumers to get a market mindset for their own power.
Absolutely.
Probably takes some time.
Yes.
A couple of questions. First of all, this was like a pilot project that done in a small.
Absolutely. It's very small. It's a research project, yeah.
As of today, like it is not legal to a power system anywhere in the province.
In the province of Ontario, it is not legal.
Except for the experimental thing.
Yeah, exactly. So in the province of Ontario and most regulatory boards, you're not allowed to set the price of electricity by yourself. So this is, you cannot do this. You must get permission.
I'm saying, like, is it legal to have like a two-way power that you can buy and sell? If you have an electric car and you want to sell power, like you store it in the night time and then sell in the daytime.
No.
So it is not legal.
No.
Anywhere outside, like in entire North America?
California, there are legislations. There's a company called eMotorWorks. So what they do is when there's lots of solar on their system, they incentivize you to charge at that time. But these are pilot projects. There's nothing mainstream in North America. There is in Europe, but not in North America.
And just to take the point the gentleman was making, so eventually in a couple of years, I don't know, like whatever the systems take over, so then will it be feasible to transport power from the generation point to the like user point using those grids?
Yeah.
So if in a rural area, like somebody is generating very cheaply, and now I'm sitting in the city, want to use it, but I'm using the transmission line of the utility.
Yeah.
So will that be possible?
Yeah, but what they'll do is they'll take this marketplace, they'll simplify it, and come from the distribution level down. So like the gentleman was mentioning, this type of energy trading happens today at the bulk level. What we're proposing to do here is bring that marketplace between the distribution utility and those DERs. In that case, the bulk power grid will never go away, at least for the next, I think, for the next 10 to 15 years. Because as soon as we have about 25 to 30% renewables on the grid, as Germany's found out, there's just too much intermittency and stability issues, right? So that bulk power grid is always going to be there. The only way we can use these DERs is in those special situations in which we have those congestion points, and then give them incentives to back off. That's the way we see it being used. But the utility very much has to be the driver. Like, I don't see these independent communities just branching off. Partly because the infrastructure that they propose is trading on is still owned by the utility.
The proposed, like Tesla is proposing the solar roofs and all that. Like,
Yeah.
And I'm presuming like it might be in the market in a year or two.
Yeah.
Then at that point of a time, there has to be a system that's able to trade, like it's a two-way power system.
So power systems are even two-way today. Like, we're still injecting power into the grid. It's just that there's no communication between your utility and you in real time to tell you to stop.
How we are injecting power in the system?
Well, let's say you have a house, right? And the house is 10 kilowatts, and at your peak it's 5 kilowatts, right? So that excess 5 kilowatts is going into the grid, right? Your neighbor might use it. It might flow down to the other end of the street. You're injecting that power into the grid. Your meter's just running backwards, right? There's a power in, if you have a solar roof, yeah. Does that answer your question?
Yeah, well,
You can't just bring infinite into the city. Right now, we're constrained coming into Toronto. That's why they built Portland's power center down inside this side of the constraints, because you melt the transmission lines that get too heavily loaded, and so you can't build new ones. So you can't get power into downtown Toronto any other way. That you need to site generation here.
Yeah.
in your opinion, in like coming, how much time like the utility will be ready for this two-way with power?
Well, with guys like that working on it, I think he's,
Well, I
you
mean,
need a mechanism to pay people. Which
yeah,
this
like,
is.
I'll give you an example. Electra, they're probably the most advanced utility in Ontario. So they've built a virtual power plant software that does something like this. And now they have a new product called Grid Exchange. And they're doing exactly this, right? They're incentivizing people to discharge at certain times. So this is a market that's heating up. But to your earlier question, will bulk power grids ever go away? I don't think so. I have a couple of slides on that later. We'll get to it.
Are they doing a blockchain?
Yes, they are.
Electra is?
And Hyperledger, yeah.
Oh.
Yeah. It's called Grid Exchange. You'll like it. Check it out. Through these, we did some off-chain simulation scenarios of 8 houses with all those assets. And what we found was if we do coordinate all these resources, what we can do is we can take that peak load and we can reduce it by 60%, mainly by getting the battery to discharge at helpful times. Right? So I think the gentleman was making points about the revenue. The revenue in this model is absolutely not enough. We see a weekly community cost reduction from $252 to $236. So that's $2 per week per house, which is nothing, right? So all this, actually, the trading, all the hype is about, hey, you can sell your energy, you can make money. In the current economics with how electricity is so cheaply priced right now, that's not true. But the flip side is that the utility doesn't need to spend $5–10 million upgrading their infrastructure. So actually the winner in all this is the utility, not necessarily the peers. So to enhance the business case, it's obvious that the utility needs to get involved and distribute more incentives for people to buy into these systems because they're the winners at the end of the day. Okay. When we add electric vehicles and we have a balance of 4 selfish and 4 helpful, and we find that we can actually reduce the peak load a little bit more, mainly because if we have 4 selfish or 8 selfish and 8 helpful, they all tend to charge at the same time, so we have the same problem. So in this case, we bring it down and we distribute, we bring it down to 47 kilowatts. So last couple of slides here. There's a lot of hype about blockchain obviating the middleman and cutting the utility out of the middle, especially over the last couple of years. People are talking about, hey, if we can trade energy with each other, then maybe we don't need the middleman, maybe we don't need the utility, including Bloomberg. There's a couple of articles. And people are making these claims, right? They're saying, okay, well, blockchain's great. We can enable these peer-to-peer energy transactions, and we can obviate the need for utilities. Number 2, let's all get solar panels and batteries. We create our own microgrids together. And number 3, I can sell my excess energy to whoever I want, whenever I want, and for whatever price. So these are the ways some people are starting to think. I just want to talk about them very briefly. Number 1, the utility actually owns the infrastructure that you're trying to trade on. So that's never going to happen, right? The utility is not just going to get out of the way. So that is not true. It's not like you can just come in and remove the utility. That's not going to happen. Number two, let's create all these microgrids. That's pretty expensive and necessary. In the coming years, with this whole transactive concept, you'll be able to take your energy and inject services back to the grid and earn money. So it's not necessary for you to go and start making these islands. There are concepts called islanded microgrids in which you can have an interconnection switch and switch off completely from the grid. That's totally like doable. But in this day and age, what you can do is actually switch on and switch off. Whenever you feel you have services to provide to the grid, you can connect to the grid. If there's an outage on the grid and you want to island off, you can island off. Still a little bit away from the business case, like maybe 3, 4, 5 years until those situations start happening. But it's coming for sure. Number 3 is this thing about I can sell energy to whoever I want. So if we have one street, let's say from that gentleman to this gentleman, and let's say 1, 2, 3, 4, 5, we have 5 houses. So house 1 makes a deal with house 5 and says, I'll give you 20 kilowatts for $2. He can't guarantee that all 20 kilowatts are going to go to him, right? You can't beat physics. The electrons are going to flow to where the demand is. So if there's demand everywhere on this feeder, everybody's going to get a piece of that 20 kilowatts. So there's no way reliably you can tell somebody that I'm going to give you 20 kilowatts and they'll get the 20 kilowatts. Instead, what we do is we use the grid as a giant buffer, right? And that buffer feeds everybody. But what we're trying to do is just control the economics around it. That's all this project is. Okay? So conclusion and future work, don't believe everything you read. Blockchains are not going to remove the need for electric utilities. In fact, we need them. Number 2, blockchains can be key enablers of transactive energy systems, and they can improve power system resiliency. And the way forward, as you know, we implemented this in Hyperledger Composer, which is actually more like a PlayStation version of where we need to be. It's not running any actual nodes. It's not running an actual consensus algorithm. It's just a proof of concept. So in our research forward with Dr. Henry Kim and Merrick, and hopefully with you going forward, we really want to get together and implement this more on nodes and evaluate the transaction latency and things like this. So that's our next step going forward. And that's it. Thank you.